What if you could step to the edge of the universe's most mysterious phenomenon, a place where gravity is so strong, not even light can escape? Picture yourself drifting toward a black hole, the fabric of space and time twisting around you like a cosmic whirlpool. One moment you're staring into infinite darkness, the next you're stretched into a single, impossibly thin strand, a process scientists call spaghettification. This isn't science fiction. It's the terrifying, awe-inspiring reality of black holes, nature's ultimate enigmas. And today, we're diving deep into 30 facts about these cosmic monsters that will shatter everything you thought you knew about space. Black holes are more than just vacuum cleaners of the universe. They're time-warping, star-eating, galaxy-shaping powerhouses that challenge our very understanding of physics. Did you know a single black hole can weigh billions of times more than our sun? Or that some spin so fast they drag the fabric of space itself into a swirling vortex? These aren't just distant curiosities, they're the architects of the cosmos, sculpting galaxies and possibly even holding the key to unlocking the universe's deepest secrets. By the time we're done, you'll see the night sky differently. You'll learn how black holes might be hiding extra dimensions, how they could one day reveal the true nature of reality, and why some scientists believe they might even be portals to other universes. So buckle up, we're about to take a journey into the heart of darkness and emerge with a mind full of cosmic wonder. Because when it comes to black holes, the truth isn't just stranger than fiction, it's more thrilling than anything we've ever imagined. Here's something that might surprise you: black holes aren't holes at all. The name is a cosmic misdirection, like calling a tornado a sky funnel. In reality, a black hole is a sphere of unimaginable density, a place where matter has been crushed down to a single, infinitely tiny point called a singularity. Think of it like taking the entire mass of a star, or sometimes billions of stars, and squeezing it into a space smaller than a grain of sand. That's why the gravity around it is so powerful, warping space and time into a bottomless well. Anything that crosses the event horizon, the point of no return, gets pulled in with no hope of escape, not even light, which is why these cosmic beasts appear pitch black against the backdrop of space. So why do we call them holes if they're actually spheres? It dates back to early theories about gravity wells, where scientists imagined space as a stretched-out fabric. A massive object like a star creates a dip in that fabric, like a bowling ball on a trampoline. But a black hole, it's like someone poked a needle straight through, creating a tear so deep nothing can climb back out. That visual stuck, even though we now know the truth. The real mind bender: from the outside, a black hole looks like a perfect dark sphere, but if you could peek inside, the laws of physics as we know them would break down entirely. Time slows to a crawl, light bends into impossible curves, and the very idea of up or down loses all meaning. And here's the twist: black holes aren't just cosmic vacuum cleaners sitting still in space. They rotate, some at nearly the speed of light, dragging spacetime around them like a whirlpool. Imagine stirring a cup of coffee with a spoon. The liquid twists as the spoon moves. Now replace the spoon with a black hole and the coffee with the fabric of the universe itself. That's the kind of distortion we're talking about. So the next time you hear black hole, picture a spinning sphere of pure gravity, a cosmic wrecking ball that bends the rules of reality, not some dark, empty tunnel in space. But what makes a black hole's grip so inescapable? The answer lies in its event horizon, the ultimate point of no return, where gravity's pull becomes unstoppable. Picture standing at the edge of a waterfall where the current grows faster and faster until there's no swimming against it. That's the event horizon, the cosmic tipping point where even light, traveling at 671 million miles per hour, loses the battle against gravity. Once you cross that invisible line, there's no going back. Not a single signal, scream, or shred of matter can ever escape. Here's the wild part: the event horizon isn't a physical barrier. It's more like a one-way door built by gravity itself. From the outside, it looks like a perfect black sphere, smooth and ominous, but step inside and space and time switch roles. Time freezes for any observer watching from a distance, while for you, falling inward, the universe ahead warps into a tunnel of distorted light and crushing forces. Scientists call this spaghettification, not just a dramatic name, but a real phenomenon where gravity stretches you into a noodle-thin strand long before you reach the center. Yet the event horizon isn't the same for every black hole. Smaller ones, like stellar mass black holes formed from collapsed stars, have horizons just miles wide, but their gravity is so intense near the edge that tidal forces would rip you apart instantaneously. Supermassive black holes, like the one at the heart of our galaxy, have horizons wider than our solar system. You could cross one of those without immediately noticing. At least until you looked back and realized the entire universe outside had narrowed into a shrinking circle of light behind you, forever cut off. And here's the twist: the event horizon isn't just a death trap, it's also a cosmic recorder. According to the holographic principle, every bit of information about what falls in gets encoded on its surface, like a fingerprint pressed into spacetime. So while the black hole devours stars, planets, or even entire galaxies, their story isn't truly lost. It's etched onto the horizon in ways physicists are still struggling to decode. That means the universe's ultimate vault might not be a pit of oblivion, but a library written in gravity itself. Crossing the event horizon is just the beginning of the nightmare, because what comes next is even more horrifying. Spaghettification isn't just a quirky scientific term. It's the gruesome reality of how a black hole's gravity tears everything apart, atom by atom. Picture this: you're falling feet first toward the singularity, and the pull on your toes is exponentially stronger than the pull on your head. The difference in gravity between those 2 points stretches you like taffy, elongating your body into a strand thinner than a spaghetti noodle over miles. Your bones would snap first, then your muscles, then even the molecules holding you together. All while you're still conscious, watching your own limbs distort into grotesque, mile-long ribbons. But here's what makes it even stranger: the process isn't instant. Near a small black hole, the tidal forces are so extreme you'd be shredded in milliseconds. But near a supermassive one, you might have agonizing seconds or even minutes to process what's happening as you're slowly pulled apart. Scientists call this the no-hair theorem, because no matter what you are, a human, a spaceship, or an entire planet, by the time the black hole's done with you, you're reduced to a featureless stream of particles, your identity erased. And here's the cruel twist of physics. From your perspective, spaghettification would feel like floating in zero gravity at first. There's no sudden yank, no dramatic snap, just an eerie, gradual realization that something's wrong. Your arms start drifting apart unnaturally, your vision blurs as your eyeballs stretch, and you'd feel a creeping tension, like every cell in your body is being gently, then violently pulled in opposite directions. By the end, you're not just dead, you're a cosmic thread, your atoms stretched across light years of warped space, destined to spiral into the singularity like water down a drain. Yet in that final moment, there's a bizarre beauty to it. The same forces that destroy you also create a surreal light show. As your body stretches, the last photons of light bouncing off your skin would get distorted into loops, circling the black hole like fireflies trapped in a jar. To an outside observer, you'd freeze at the event horizon, fading to red, then vanishing. But for you, the universe would collapse into a single, blinding point ahead, while behind you, all of time and space crumples into a shrinking pinprick of light. It's the most violent death imaginable, and also the most poetic. The universe doesn't just kill you, it turns you into art. If you think time always ticks at the same steady pace, a black hole has a brutal reality check for you. Near these gravitational monsters, time doesn't just slow down. It warps into something unrecognizable, like a clock melting in a nightmare. This isn't science fiction. It's Einstein's theory of relativity in action, proving gravity doesn't just pull on objects, it bends the very fabric of time itself. Picture this: for someone falling toward a black hole, minutes might pass, but for observers watching from a safe distance, years could go by. It's the ultimate cosmic time machine, where the universe's rules twist into something stranger than any movie plot. Remember the scene in Interstellar where hours on the watery planet near Gargantua equal decades back on Earth? That wasn't just Hollywood drama. The film's science advisor, Nobel Prize-winning physicist Kip Thorne, based that time dilation on real equations. The closer you get to a black hole's event horizon, the more extreme the effect becomes. Gravity's grip stretches time like taffy, slowing its passage relative to the rest of the universe. For a spacecraft orbiting just outside the danger zone, clocks would tick noticeably slower than those on Earth. Miss a single orbit, and you might return to find everyone you knew has aged decades without you. But why does this happen? Einstein revealed that time and space aren't separate. They're woven together into a single fabric called spacetime. A black hole's gravity creates a steep well in that fabric, and just as a ball rolling down a hill speeds up, time itself flows faster or slower depending on where you are in that warped landscape. Near the black hole, you're essentially crawling through the deepest part of the slope while everyone else is still strolling on flat ground, the craziest part. This isn't an illusion. Your watch literally ticks slower. Your heart beats fewer times per outside minute. Even the light you emit stretches into longer, redder wavelengths, a phenomenon called gravitational redshift. Here's where it gets even wilder. If you could hover just above the event horizon without being torn apart, time for you would nearly stop compared to the universe around you. Peer outward and you'd see stars whirling like a sped-up film, galaxies evolving in fast forward, until eventually the entire cosmos outside would fade into darkness as the universe itself ages to death around you. Meanwhile, for anyone watching you, your image would freeze at the horizon, redden and dim, as if you were turning into a ghost trapped in time. It's a paradox too. From your perspective, you'd cross the horizon in finite time, but to the outside universe, you never truly do. The black hole doesn't just consume matter, it steals time itself. So next time you check your watch, remember, time isn't the constant we think it is. It's fluid, shaped by gravity's invisible hands, and nowhere is that more obvious than at the edge of a black hole where the universe's most precise clocks would surrender to the void's slow, relentless drag. Not all black holes sit motionless in space. Some spin so fast, they twist the very fabric of reality into knots. These cosmic whirlpools, known as Kerr black holes, rotate at speeds approaching the universe's ultimate speed limit, light itself. Picture a figure skater pulling their arms in to spin faster, except here, the skater is a collapsed star with the mass of 1,000 suns, and its rotation warps spacetime into a swirling vortex. The result, a maelstrom of gravity so extreme, it drags everything nearby, even empty space, into a relentless, inescapable spiral. What makes these spinning black holes so bizarre isn't just their speed, it's how they distort the rules of physics around them. Imagine stirring honey with a spoon. The liquid clings to the utensil, creating whirls and eddies. Now replace the honey with space-time and the spoon with a black hole spinning millions of times per second. This effect, called frame dragging, means that near a Kerr black hole, you couldn't stay still even if you tried. Space itself is being pulled around like a cosmic treadmill, forcing planets, stars, and even light to orbit in the same direction as the spin. The numbers behind this are staggering. Some supermassive black holes rotate at 95% the speed of light, their event horizons whipping around at over 500 million miles per hour. At that rate, a single day on a black hole could be shorter than a blink, but for an outside observer, time near its edge would crawl to a near standstill. And just like a whirlpool in water, the faster it spins, the deeper the distortion. Close enough, the black hole's rotation could twist spacetime into a donut-shaped zone called the ergosphere, where not even light can move against the current. Here's where it gets even wilder. A spinning black hole doesn't just trap matter. It can fling it back out with unimaginable force. Particles caught in the ergosphere might steal energy from the black hole's rotation, getting hurled away at relativistic speeds in jets that stretch across galaxies. These jets, visible across the universe as beams of intense radiation, are cosmic fingerprints of a black hole's spin, a proof that these monsters aren't just consuming matter, but actively reshaping their surroundings. Yet the true mind-bender is what happens if you could survive a plunge into one. Unlike a stationary black hole where gravity crushes you into a point, a Kerr black hole spin might offer a temporary reprieve. Some theories suggest its rotation could warp spacetime so severely that the singularity becomes a ring, a gateway to other universes or distant corners of our own. Of course, you'd still be spaghettified long before reaching it, but the idea hints at something profound. A spinning black hole isn't just a destroyer. It's a cosmic transformer, turning the raw power of gravity into a dynamic, universe-altering force. So the next time you hear about a black hole, don't picture a static void. Think of a gravitational dynamo spinning at the edge of physics, where space and time are no longer straight lines, but a spiraling dance of chaos and possibility. Deep in the heart of our Milky Way, hidden behind thick clouds of cosmic dust, lurks a monster so massive it defies human comprehension: Sagittarius A, the supermassive black hole anchoring our galaxy. With a weight equal to 4 million suns crushed into a space smaller than our solar system, this gravitational titan doesn't just sit idle. It's the invisible conductor of a galactic symphony, orchestrating the orbits of billions of stars with its relentless pull. Think of Sagittarius as the sun at the center of a colossal merry-go-round, except instead of children on horses, its entire star system's whirling around it at thousands of miles per second. Stars like S2, one of the closest known to orbit the black hole, hurtle so fast that they complete a full lap in just 16 years, a cosmic sprint that would take our solar system over 200 million years to match. Yet even at those breakneck speeds, nothing escapes the black hole's grasp. Its gravity shapes the Milky Way's spiral arms, influencing everything from the birth of new stars to the paths of wandering planets. Here's what's truly mind-blowing. Despite its staggering mass, Sagittarius A is shockingly quiet compared to other supermassive black holes. Some of its counterparts in distant galaxies blast energy across the cosmos, devouring stars like celestial sharks in a feeding frenzy. Ours, by contrast, is more like a sleeping giant, occasionally snacking on passing gas clouds but mostly lurking in the shadows. That changed in 2019 when scientists captured its silhouette for the first time using the Event Horizon telescope, revealing a haunting ring of light bending around the abyss. But don't let its calm demeanor fool you. The black hole's influence is everywhere. Without it, the Milky Way as we know it wouldn't exist. Stars like our sun trace graceful loops around it, held in balance by its gravity even as they drift through the galaxy's spiral arms. Some researchers even suspect Sagittarius A played a role in our solar system's formation, its gravitational nudges helping to stir the primordial cloud that birthed our sun and planets. And here's the kicker: we're not just orbiting this beast, we're falling toward it. Right now, our solar system is locked in a slow, cosmic spiral toward the galactic center, pulled by Sagittarius A's inexorable gravity. Don't panic, though. At our current speed, we won't get close for billions of years, long after the sun has died and Earth has frozen over. Until then, this silent colossus will keep ruling the Milky Way from the shadows, a reminder that even in the vast emptiness of space, nothing truly moves without gravity's unseen hand. The universe might be teeming with black holes too small to see, ancient relics from the very first moments of creation. These hypothetical cosmic specks, known as primordial black holes, could have formed in the chaos of the Big Bang when dense regions of the newborn universe collapsed under their own gravity. Unlike the massive black holes we observe today, these could be as light as a paperclip or as heavy as a mountain, packing all that mass into spaces smaller than an atom. Imagine trillions of them drifting unseen through the cosmos like invisible ghosts, each a frozen remnant of the universe's violent infancy. What makes this idea so compelling is that these tiny black holes could solve one of astronomy's biggest mysteries, dark matter. Scientists know this invisible substance outweighs visible matter 5-to-1, shaping galaxies with its gravity, but they've never directly detected it. Primordial black holes, if they exist, might be the missing piece. Picture the Milky Way's halo not as a cloud of exotic particles, but as a swarm of these minuscule gravitational traps, their collective pull bending starlight and guiding the motions of stars. Some theories suggest they could even explain bizarre cosmic events, like stars flickering as if something passed in front of them. Not a planet or dust cloud, but a tiny black hole warping the light like a lens. Yet the hunt for these elusive objects is a cosmic detective story with more twists than a black hole's event horizon. If they're too small, they'd have evaporated by now due to Hawking radiation, a process where black holes slowly lose mass by emitting particles. But if they're just the right size, say around the mass of an asteroid, they could still be lurking everywhere, occasionally betraying their presence by distorting light or even emitting faint bursts of radiation as they consume stray atoms. Some researchers are scanning old photographic plates for unexplained flashes, while others listen for the echoes of black holes colliding in space, hoping to catch the whisper of a primordial relic. The wildest possibility, one might be closer than we think. If a primordial black hole wandered into our solar system, its gravity could tug on planets in ways no visible object could explain. It might even pass through Earth itself, leaving a needle-thin trail of superheated rock as atoms spiral into its microscopic maw. You wouldn't see it coming, just a sudden tremor, a strange heat signature, and then nothing. Whether they're out there or not, the idea challenges everything we assume about black holes. They're not just star-crushing behemoths. They could also be the universe's smallest, most ancient secrets hidden in plain sight, rewriting the rules of gravity and maybe, just maybe, holding the key to the dark matter puzzle. Stephen Hawking flipped our understanding of black holes on its head with one radical idea: they aren't eternal. In 1974, the legendary physicist proposed that these cosmic monsters don't just devour everything in their path, they also slowly leak energy, fading away like fog under sunlight. This phenomenon, now called Hawking radiation, revealed something shocking. Given enough time, even the mightiest black hole can vanish without a trace. Here's how it works. Quantum mechanics tells us empty space isn't truly empty. It's a seething sea of virtual particles that blink in and out of existence too quickly to detect. Normally, these particle pairs annihilate each other instantly, but near a black hole's event horizon, things get twisted. Gravity's pull can yank one particle inward while its partner escapes, stealing a tiny bit of the black hole's energy in the process. Over billions of years, this slow leak adds up, draining the black hole's mass until poof, it dissolves in a final burst of high-energy particles. The implications are staggering. Before Hawking, black holes were thought to be one-way streets growing forever as they swallowed stars and gas. Now we know they have an expiration date. A typical stellar mass black hole might take 10 to the power of 67 years, that's a 1 followed by 67 zeros, to fully evaporate, supermassive ones. They'd outlast every star in the universe, taking incomprehensibly longer to dissipate. But the principle remains: no black hole is truly permanent, yet there's a haunting twist to this theory. When a black hole evaporates, what happens to everything it swallowed? Stars, planets, even entire civilizations. their information seems lost forever, violating quantum mechanics' rule that information can't be destroyed. This black hole information paradox has spawned decades of debate, with Hawking himself famously changing his stance multiple times. Some physicists argue the data gets scrambled and radiated back out in Hawking particles like smoke carrying the ashes of burned books. Others propose wilder ideas like hidden universes inside black holes where the information is preserved. The craziest part, we might never observe Hawking radiation directly. For a black hole the mass of our Sun, the radiation would be trillions of times weaker than the cosmic microwave background, utterly drowned out by the universe's noise. But in a brilliant workaround, scientists have recreated black hole conditions in labs using supercooled fluids or laser beams, observing artificial event horizons where Hawking-like radiation appears. These experiments suggest the theory holds up, even if we can't yet point a telescope at a real black hole and see its glow. So while black holes might reign for epochs longer than human comprehension, they're not invincible. Given enough time far beyond the lifespan of stars, galaxies, or even protons, the universe's darkest monsters will whisper themselves out of existence, leaving behind only faint ripples of heat in an otherwise silent cosmos. It's a humbling thought. In the end, nothing, not even gravity's ultimate trap, escapes the slow unraveling of time. Hollywood loves to portray black holes as cosmic vacuum cleaners, relentlessly sucking in everything around them, but the truth is far stranger. Despite their terrifying reputation, these gravitational giants don't actively pull matter in like some interstellar Hoover. In reality, a black hole behaves more like a bottomless well in the fabric of spacetime. If you replaced our Sun with a black hole of the same mass, Earth wouldn't get sucked in. Instead, our planet would continue orbiting peacefully, just in perpetual darkness. The only way to fall into a black hole is to venture too close to its event horizon, the point where gravity's grip becomes inescapable. So why the misconception? It's all about perspective. Imagine standing near a waterfall. The water isn't actively pulling you in, but if you step too close to the edge, the current takes over. Black holes work the same way. Their gravity is no stronger than a star of equal mass until you cross that invisible boundary. Take the supermassive black hole at our galaxy's core, Sagittarius A. Stars like S2 whip around it at blistering speeds, just as they would orbit any dense object of that mass. They're not being sucked inward. They're following the natural curve of spacetime, like marbles rolling around a funnel. Here's where it gets fascinating. Matter rarely falls straight into a black hole. Instead, it spirals in gradually, forming what's called an accretion disk, a superheated whirlpool of gas, dust, and doomed stars. Friction within this disk heats material to millions of degrees, causing it to glow brighter than entire galaxies. But even here, the black hole isn't actively pulling. Particles collide, lose energy, and slowly drift inward over centuries, like leaves circling a drain. Only when something strays within a few dozen miles of the event horizon does the real drama begin, as tidal forces stretch and compress it beyond recognition. One of the best proofs that black holes don't indiscriminately suck comes from our own cosmic neighborhood. The Milky Way is littered with stars and gas clouds passing near Sagittarius A, yet most escape unscathed. Even when a star gets torn apart by tidal forces, a process called a tidal disruption event, only about half its material actually crosses the horizon. The rest gets flung back into space in spectacular jets, defying the vacuum cleaner stereotype. This subtlety reveals a deeper truth about gravity. Einstein showed it's not a force in the traditional sense, but the curvature of spacetime itself. A black hole doesn't reach out and grab things. It simply bends the stage so severely that anything straying too far stage left past the event horizon can't find its way back. So next time you see a sci-fi black hole devouring a spaceship with a dramatic whoosh, remember, in reality, you'd have to steer yourself into oblivion. The universe's ultimate trap doesn't chase its prey. It waits patiently for the unlucky few to cross its threshold. At the far reaches of the observable universe, a black hole so colossal exists that it defies all sense of scale, ton 618. This cosmic leviathan weighs in at 66 billion times the mass of our Sun, making Sagittarius A look like a mere pebble by comparison. To grasp its sheer immensity, picture our entire solar system, every planet, comet, and speck of dust out to the Kuiper belt, and then imagine something over 1,000 times wider. That's the diameter of ton 618 event horizon, a gravitational maw so vast it could swallow 11 of our solar systems lined up end to end without breaking a cosmic sweat. But size isn't the only thing that makes this black hole terrifying. Its appetite matches its proportions. The accretion disk circling ton 618, a superheated maelstrom of doomed gas and stars, shines with the brightness of 100 trillion suns, outshining every star in the Milky Way combined. This isn't just a black hole, it's a quasar, a beacon of destruction visible across billions of light years. The energy radiating from its disk is so intense that if it replaced our Sun, Earth would be vaporized in an instant, its atmosphere stripped away by the force of 1,000 hurricanes made of pure radiation. Here's the twist: ton 618 isn't just a relic from the early universe, it's a living puzzle. Black holes this massive shouldn't exist under current theories of cosmic growth. Even if one started as a giant seed after the Big Bang, it would need to consume stars at an impossible rate for billions of years to reach this size. Yet there it sits, challenging our understanding of how the universe builds its most monstrous structures. Some scientists speculate it might be the result of multiple black holes merging in a cosmic collision, a fate that could await our own galaxy when it smashes into Andromeda billions of years from now. The most humbling thought: ton 618 isn't alone. Lurking in the depths of space, even larger black holes might await discovery, their event horizons stretching across distances so vast they redefine our notion of big. These aren't just celestial objects, they're gravitational empires, ruling over galaxies with an invisible fist, reminding us that in the grand theater of the cosmos, even the mightiest stars are just fleeting specks in the shadow of giants. Black holes don't just consume, they collide, and when they do, the universe itself shudders. On September 14, 2015, scientists witnessed something unprecedented: the faint echo of two black holes, each about 30 times the mass of our Sun, spiraling toward each other over billions of years before finally merging in a cataclysmic embrace. The energy released in that final second was so immense, it warped the fabric of spacetime itself, sending ripples across the cosmos at the speed of light. Those ripples, called gravitational waves, washed over Earth, stretching and squeezing our planet by a fraction of an atom's width, a signal so subtle it took the Laser Interferometer Gravitational Wave Observatory, or LIGO, to catch it. Think of spacetime as the surface of a still pond. Drop a pebble and circular waves ripple outward. Now imagine two heavy stones orbiting each other, faster and faster, until they smash together with a splash. That's essentially what happens when black holes merge, except instead of water, the waves ripple through the very framework of reality. The more massive the black holes, the bigger the splash. Some collisions, like the one detected in 2017 involving black holes 60 and 30 solar masses, release more energy in gravitational waves than all the stars in the observable universe emit in light during that same moment. Here's the mind-bending part: these waves aren't just cosmic curiosities, they're literal distortions of space and time. As they pass through Earth, they briefly alter the distance between objects, stretching your body one way while compressing it the other, like taffy in an invisible cosmic tug-of-war. Of course, the effect is so tiny you'd never feel it, but the fact we can measure it at all is a triumph of human ingenuity. LIGO detectors, with their laser beams traveling down 2.5-mile long vacuum tubes, can spot changes 10,000 times smaller than a proton, sensitive enough to hear the universe whispering its secrets across billions of light years. These mergers also solve a cosmic mystery: how black holes grow so monstrously large. Every collision is a gravitational upgrade, a way for black holes to pack on mass without swallowing a single star. The two black holes that created that first detected wave likely began as massive stars that collapsed and then spent eons circling each other in a slow death spiral, radiating away energy as gravitational waves until finally their event horizons touched. At that instant, their singularities fused into one, creating a new black hole with a mass slightly less than the sum of its parts, the missing mass, converted directly into the energy of those spacetime ripples, proving Einstein's equation E equals mc squared in the most violent way imaginable. Yet the aftermath is strangely beautiful. The newborn black hole doesn't settle quietly. It rings like a struck bell, vibrating as it sheds imperfections in a final burst of gravitational waves. Scientists call this the ring down, and it's the smoking gun that confirms the merger happened. By studying these signals, researchers can reconstruct the black hole's masses, spins, and even the orientation of their orbits, turning gravitational waves into a new kind of astronomy. No longer limited to observing light, we can now listen to the universe's hidden symphonies, the crashes and echoes of its most enigmatic objects playing out in the dark. And the discoveries keep coming. In 2019, LIGO and its European counterpart Virgo detected a merger so lopsided it defied expectations. A black hole 23 times the Sun's mass swallowing a neutron star just 2.5 times heavier than our Sun. The event, dubbed GW 2194, sent ripples through the scientific community, offering clues about how black holes and neutron stars, the densest objects in existence, interact. Each new detection paints a richer picture of a universe teeming with invisible collisions, where black holes dance, merge, and reshape the cosmos in ways we're only beginning to understand. So the next time you gaze at the night sky, remember, the darkness isn't silent. It's alive with the echoes of distant cataclysms, each one a ripple in the pond of space-time, a fleeting signature of the universe's most violent and spectacular weddings. At the edge of the observable universe, some black holes don't just lurk in darkness, they light up the cosmos with the brilliance of a trillion suns. These are the engines behind quasars, the most luminous objects in existence, outshining entire galaxies with their blinding glare. Imagine taking the energy output of every star in the Milky Way, compressing it into a single point, and then multiplying that by 1,000. That's the raw power of a quasar, all generated by a supermassive black hole in the throes of an insatiable feeding frenzy. What makes these cosmic beacons possible isn't just the black hole itself. It's the chaotic whirlpool of matter spiraling into oblivion. As gas, dust, and even entire stars get pulled toward the event horizon, they don't go quietly. Friction heats this material to millions of degrees, transforming the accretion disk into a swirling furnace of plasma brighter than anything else in the universe. Magnetic fields twist this superheated soup into jets that shoot outward at nearly light speed, carving paths through intergalactic space like cosmic blowtorches. The result, a light show visible across billions of light years, a testament to gravity's ability to create as well as destroy. Quasars aren't just spectacular, they're time capsules. Because light takes time to reach us, the quasars we observe today are snapshots of the ancient universe, some dating back to when the cosmos was just 1 billion years old. Their existence so early poses a puzzle. How did black holes grow so massive so quickly? Current theories suggest they started as seeds from collapsed giant stars or dense gas clouds, then ballooned in size by gorging on the plentiful material of the young universe. Their radiation likely played a crucial role in shaping early galaxies, their fierce winds blowing away loose gas to halt star formation and sculpting the galactic landscapes we see today. Here's the twist: every quasar is a phase, not a permanent state. As a black hole consumes the surrounding gas, the fireworks eventually dim. Our own Milky Way center might have been a quasar billions of years ago, its active days long past. Yet even now, distant quasars serve as lighthouses in the cosmic dark, their light encoding secrets about the universe's youth and proving that even the darkest objects can become the brightest beacons. Crossing the event horizon of a black hole sounds like an instant death sentence, but what if the reality is stranger? For small black holes, the tidal forces near the edge would shred you apart in microseconds. But step toward a supermassive black hole like Sagittarius A, and the rules change. The sheer size of its event horizon, millions of miles across, means the difference in gravity between your head and feet could be negligible at first. You might not even realize you've crossed the point of no return until it's too late. Inside, physics as we know it unravels. Time and space swap roles, making forward synonymous with toward the singularity. Light from the outside universe would warp into a blinding halo above you, while below, the black hole's crushing grip grows stronger with every passing second. Some theories suggest the tidal forces would still kill you eventually, but not immediately. You'd have a brief window, maybe minutes or hours, to witness the laws of physics bend into unrecognizable shapes. The real controversy lies in whether your brain could process the experience at all. Time dilation near the singularity becomes so extreme that your final moments might stretch subjectively into years. To an outside observer, you'd appear frozen forever at the horizon, but for you, the universe outside could blink through its entire future before you hit the point of spaghettification. It's a paradox. Both outcomes seem true simultaneously. You'd die in a flash, and yet, from your perspective, live long enough to watch the cosmos age and die around you. This isn't just speculation, it's a frontier of active debate. Some physicists argue quantum effects might create a firewall of energy at the horizon, vaporizing anything that crosses. Others propose a gentler fate where you'd simply become part of the black hole's quantum information, encoded on its surface like data on a cosmic hard drive. The truth might lie beyond our current theories, in a realm where relativity and quantum mechanics finally reconcile. The wildest implication: if black holes truly preserve information, your journey inward might not be destruction, but transformation. Every atom, every memory, every spark of consciousness could be rewritten into the fabric of the black hole itself, a fate as enigmatic as the singularity waiting at its heart. So while survival might be fleeting, the physics of a supermassive black hole offers something even more profound: a glimpse into the universe's most forbidden frontier. If black holes are the universe's ultimate vacuum cleaners, sucking in everything that dares to get too close, then white holes are their cosmic opposites, hypothetical fire hydrants blasting matter outward with unstoppable force. These bizarre theoretical objects, first proposed as mathematical solutions to Einstein's equations, would behave like black holes running in reverse. Instead of an event horizon that traps everything inside, a white hole would have a one-way exit door, violently expelling light, gas, and anything else that came near it. Picture trying to push a beach ball underwater with all your strength, only to have it rocket back to the surface the moment you let go, except in this case, the ball is entire stars' worth of energy, and the water is the fabric of spacetime itself. What makes white holes more than just a physicist's thought experiment is their potential connection to wormholes, the hypothetical tunnels through spacetime often seen in science fiction. Some theories suggest that a black hole's singularity might connect to a white hole elsewhere in the universe, or even in another universe entirely, forming a bridge between distant points in space and time. In this scenario, anything falling into the black hole could emerge from the white hole light years away, like a cosmic subway system with the black hole as the entrance and the white hole as the exit. The catch, the gravitational forces at play would likely shred any object attempting the journey long before it reached the other side. The real controversy surrounding white holes isn't whether they're mathematically plausible they are, but whether nature could actually produce one. Black holes form when massive stars collapse under their own gravity, but there's no known astrophysical process that would naturally create a white hole. Some researchers speculate they could be the other end of a black hole's lifespan, erupting into existence if a black hole somehow avoids complete evaporation via Hawking radiation. Others suggest they might only have existed in the extreme conditions of the early universe, flickering into existence for brief moments before collapsing or transforming into something else entirely. One of the most tantalizing possibilities is that white holes could explain certain mysterious cosmic explosions. In 2006, astronomers detected a gamma ray burst so energetic that its light had traveled for nearly 13 billion years to reach us longer than the age of most known black holes. Some theorists have floated the idea that this could have been a white hole detonating, a one-time event where a trapped region of spacetime violently reopened, releasing pent-up energy like a cork popping from a champagne bottle. Of course, mainstream astronomy favors more conventional explanations, like the collision of neutron stars, but the fact that white holes remain a plausible fringe theory shows just how much we still don't understand about the universe's most extreme phenomena. Even if white holes don't exist in reality, studying them forces physicists to confront deep questions about time, entropy, and the nature of singularities. They're a reminder that the universe's rulebook might have pages we haven't even glimpsed yet, where gravity's laws twist into strange new shapes, and the line between science and speculation blurs like starlight at the edge of a black hole's shadow. Black holes might be silent in the vacuum of space, but their collisions produce cosmic symphonies, ripples in spacetime so powerful we can actually hear them. In 2015, scientists at LIGO made history by converting gravitational waves from two merging black holes into sound waves, turning raw data into an eerie, otherworldly chirp. That fleeting audio clip, just a fraction of a second long, revealed something astonishing. The universe speaks in vibrations deeper than any orchestra could replicate. Here's how it works. When black holes spiral toward each other, their immense gravity distorts spacetime like a drumhead being struck. As they get closer, the frequency of these distortions increases, creating a rising tone akin to a slide whistle accelerating toward a climax. At the moment of collision, the pitch peaks, what scientists call the chirp, followed by a fading ringdown as the new, merged black hole settles into its stable form. The result, a sound so distinct, researchers can pinpoint the masses of the black holes involved just by listening. A lighter pair might produce a high-pitched bird-like tweet, while colossal mergers resonate like a cosmic bass note shaking the universe's foundations. But there's a twist. These waves aren't sound in the traditional sense. In space's airless void, there's no medium for sound waves to travel. Instead, LIGO team mathematically translated the gravitational wave frequencies, some as low as 50 Hz, others soaring to 1,000 Hz, into audible ranges our ears can process. The effect is haunting, like the universe itself whispering secrets through a crack in reality. The original chirp from that first detection, WGW150914, lasts just 20 milliseconds, but it carries the energy of 3 suns converted purely into spacetime vibrations. The implications go beyond novelty. By studying these songs, astronomers can reconstruct entire cosmic events they'll never see with telescopes. The pitch reveals the black hole's masses, the duration hints at their distance, the harmonics expose their spins. It's forensic astronomy, where every chirp, every warble, is a fingerprint of cataclysmic violence unfolding in the dark. Some mergers even produce overtones, secondary frequencies that ring like echoes, hinting at the newborn black hole's shape and stability. Perhaps the most poetic discovery is how common these cosmic melodies are. Since that first detection, LIGO and its sister observatories have captured dozens of black hole duets, each with its own acoustic signature. One collision in 2019, GW190521, produced a chirp so clean it sounded like a perfect musical glissando. Another, involving a black hole and a neutron star, emitted a strange, stuttering crescendo as the neutron star was shredded before vanishing into the abyss. These sounds aren't just data, they're the universe's most primal music, composed by gravity itself. So next time you gaze at the night sky, remember, the darkness isn't silent. It's a concert hall where black holes perform symphonies of spacetime, their gravitational waves humming tunes we're only beginning to understand. And with every new chirp, we're tuning into a channel older than light itself, one that broadcasts the universe's most violent, beautiful collisions directly to our ears. For decades, black holes existed only in equations and artists' renderings until April 10, 2019, when humanity finally stared into the abyss and saw it staring back. That's the day the Event Horizon Telescope unveiled the first real image of a black hole, capturing the supermassive monster at the heart of Galaxy Messier 87, 55 million light-years away. The photograph revealed something surreal, a fiery orange donut of light swirling around a perfect circle of darkness, the shadow of the black hole's event horizon. This wasn't just a scientific achievement, it was like catching a glimpse of the universe's best-kept secret. That glowing ring tells a story written in light and gravity. The photons you see are actually from superheated gas circling the black hole at nearly the speed of light, twisted into a loop by spacetime's curvature. Einstein predicted this exact effect over a century ago, light bending so severely it creates a halo around the void. But seeing it in reality was like watching a ghost step out of a chalkboard equation. The darker center, that's the black hole's shadow, a region where gravity wins so completely, not even light can escape to reach our telescopes. What's astonishing isn't just the darkness, but its size. The shadow appears 2.5 times wider than the actual event horizon, a visual illusion caused by the black hole magnifying its own silhouette through gravitational lensing. To grasp the scale of this achievement, picture stitching together a photo of a DVD on the moon using telescopes scattered across Earth. The Event Horizon Telescope pulled off something even harder, linking 8 observatories worldwide into a virtual dish the size of our planet, with resolution sharp enough to spot a golf ball on Pluto. Each night of observation generated so much data, it had to be flown on hard drives from mountaintops to supercomputers because uploading it would have taken years. The team spent 2 years crunching numbers, filtering out noise, and cross-checking results before daring to claim they'd captured the impossible. Yet the image holds mysteries deeper than the black hole itself. Why is one side of the ring brighter? That's the Doppler effect in action. The gas on the side spinning toward us appears hotter and brighter, while the receding side dims. The asymmetry also confirms M87's black hole spins, dragging spacetime around it like a whirlpool, and that hazy, uneven glow, evidence of magnetic fields churning the accretion disk into a storm of plasma, fueling jets that shoot outward for thousands of light-years. The photo's true triumph isn't just proving black holes exist, it's revealing how they shape their surroundings. Every flicker in that orange ring encodes the physics of extreme gravity, a laboratory for testing relativity where the stakes are cosmic. Future images might catch the ring wobbling as the black hole consumes stars, or even reveal the shadow's changes over time, like a slow-motion movie of spacetime itself twisting. For now, that single snapshot stands as a testament to human curiosity, a flicker of light against the dark, whispering that even the universe's most secretive monsters can't hide forever. Black holes might not be the bottomless pits they appear to be. Instead, they could be cosmic holograms, their secrets written in 2 dimensions rather than 3. This mind-bending idea, known as the holographic principle, suggests everything that falls into a black hole, every atom, photon, or even an entire star, leaves an imprint on its event horizon like data etched onto the surface of a hard drive. Imagine taking a three-dimensional object and compressing its entire essence into a flat, two-dimensional painting without losing any detail. That's the essence of this theory. The universe's most destructive objects might also be its most efficient archivist. The holographic principle emerged from a fiery debate over one of physics' greatest paradoxes. What happens to information when it vanishes into a black hole? Quantum mechanics insists information can never be destroyed, yet black holes seem to erase it completely, until physicist Leonard Susskind proposed a revolutionary fix. Just as a hologram stores a 3D image on a 2D surface, a black hole might encode everything it swallows in vanishingly tiny bits on its horizon. Each particle's properties, mass, spin, charge, could be translated into a pattern of quantum fluctuations on this spherical canvas, a cosmic ledger preserving the universe's accounting. Here's where it gets stranger. If this principle holds, the event horizon isn't just a boundary, it's a screen projecting the illusion of depth. The black hole's interior, with its crushing singularity and warped spacetime, might be a kind of cosmic mirage, a 3D projection arising from quantum interactions on its 2D surface. Think of it like watching a movie. The images seem to have depth and motion, but they're ultimately just patterns of light on a flat screen. Similarly, our perception of the black hole's volume could be an elaborate trick of physics, with the real action unfolding on its outer shell. Evidence for this idea comes from an unexpected source, entropy. In the 1970s, Jacob Bekenstein calculated that black holes possess entropy, a measure of hidden information proportional to their horizon's area, not their volume. This defied intuition, since entropy typically scales with volume in everyday objects. But if the holographic principle is correct, it makes perfect sense. The entropy reflects the data packed onto the surface, like a celestial QR code storing the black hole's entire history. Later, string theorists like Juan Maldacena showed how certain mathematical models of universes could be perfectly described by physics operating on their boundaries, a tantalizing hint that reality itself might be a hologram. The implications are staggering. If black holes are holograms, the entire universe might be too. Our 3D reality, with its galaxies, stars, and even your morning coffee, could be a projection from a hidden 2D layer at the edge of spacetime. This isn't just philosophy, it's a testable hypothesis. Physicists are analyzing gravitational wave data from black hole mergers, searching for faint echoes that might reveal quantum structure on the horizon. Others are simulating black holes in labs using ultra-cold atoms, watching for holographic signatures in their behavior. Yet the principle raises as many questions as it answers. How does the information etched on the horizon reconstruct the objects that fell in? Does consciousness or even time emerge from this flat code? And if the universe is a hologram, who or what is holding the projector? For now, these mysteries linger at the frontier of physics, where black holes serve as both puzzles and guides, their dark surfaces shimmering with secrets we're only beginning to decode. Black holes don't just swallow matter, they also fire it back into space at speeds so fast even light struggles to keep up. These cosmic cannons, known as relativistic jets, blast from the black hole's poles at nearly the speed of light, shooting superheated plasma across millions of light years like celestial lightning bolts. Picture a gargantuan particle accelerator, but one built by nature itself, where magnetic fields and gravity conspire to launch storms of energy so powerful they outshine entire galaxies. How does something known for devouring everything manage to spit matter outward? The secret lies in the chaos of the accretion disk. As gas, dust, and stars spiral toward the event horizon, friction heats them into a swirling, magnetized plasma. Some of this material doesn't make it in. Instead, the black hole's rotation and twisted magnetic fields funnel it toward the poles, where it's accelerated to nearly light speed and shot into space in two narrow, opposing beams. These jets don't just trickle out, they erupt with the energy of a million supernovas, punching through galaxies and leaving behind glowing scars in the intergalactic medium. Some of the most dramatic examples come from quasars, where supermassive black holes generate jets so intense they're visible across the observable universe. But smaller black holes produce them too. When the black hole in the binary system SS433 feeds off its companion star, it fires jets that wiggle like a garden hose on full blast, a sign of the black hole's wobbling spin. And then there's M87's famous jet, captured in stunning detail by the Event Horizon Telescope, a 5,000 light-year long beam of plasma, its knots and bends telling the story of eruptions spanning millennia. These jets aren't just spectacular, they're cosmic delivery systems spreading heavy elements forged in stellar explosions far beyond their host galaxies. Some researchers even suspect they play a role in kickstarting star formation, their shockwaves compressing gas clouds into stellar nurseries. Yet their most terrifying cousins are gamma-ray bursts, the universe's most violent explosions, thought to occur when a dying star collapses into a black hole, focusing its energy into twin jets that, if pointed at Earth, could strip our atmosphere away in seconds. Thankfully, these death beams are rare, but they serve as a reminder. Black holes aren't just passive traps, they're cosmic powerhouses shaping the universe as much as they consume it. Billions of years from now, when the last stars have burned out and galaxies fade to darkness, black holes may inherit the universe. This grim cosmic prophecy, known as the black hole era, paints a future where these gravitational titans become the sole rulers of a cold, exhausted cosmos. Picture a time so far ahead that the universe is 100 trillion times older than it is today. A desolate expanse where black holes aren't just rare anomalies, but the only remaining structures in a sea of endless night. The road to this dark era begins with the death of stars. Over the next trillion years, galaxies will exhaust their gas reserves, leaving no fuel for new stars to ignite. Existing stars will flicker out one by one, red dwarfs clinging to life the longest, their faint glow persisting for tens of trillions of years before finally sputtering into cold, dark husks. Planets will freeze, their orbits decaying as gravitational waves sap energy from their systems. Even the protons that make up atoms, once thought indestructible, may eventually decay, an unverified but theoretically possible event that would dissolve all remaining matter into subatomic particles over incomprehensible timescales. Yet through all this, black holes endure. Isolated from the universe's decay by their event horizons, they'll drift through the void like celestial tombstones, growing ever so slightly as they swallow stray particles of dark matter or the rare cosmic ray. Even then, their reign won't last forever. Thanks to Hawking radiation, even the mightiest black holes will slowly evaporate, but we're talking time frames that make the current age of the universe seem like the blink of an eye. A black hole with the mass of our Sun would take 10 to the power of 67 years to vanish. For the supermassive ones anchoring galaxies, multiply that number by 1 trillion. The final act might be the eeriest of all. As the last black holes evaporate, the universe could enter the so-called dark era, a state of near-perfect equilibrium where space is an almost featureless void, dotted only by the rarest particles separated by distances so vast that interactions become statistically impossible. No stars, no planets, no light, just a faint afterglow of radiation from long-dead black holes, cooling toward absolute zero. Some theories even suggest that quantum fluctuations in this near-empty cosmos could eventually spawn new Big Bangs, birthing fresh universes in an endless cycle of death and rebirth. But here's the paradox: this bleak future also holds a strange kind of beauty. Black holes, often seen as destroyers, might be the universe's archivists preserving information in their holographic horizons long after everything else has crumbled to dust. Their slow demise could even provide the spark for whatever comes next, seeding new cosmic beginnings with the remnants of the old. So while they herald the end of our universe's vibrant era, they might also be the key to its most distant rebirth, a reminder that in the grandest scales of time, even darkness is just a prelude. Black holes might hold the key to one of humanity's wildest dreams, time travel. The idea isn't just science fiction. It's rooted in the bizarre physics of Einstein's general relativity, where spacetime isn't a rigid stage but a flexible fabric that can twist, tear, and even fold back on itself. At the heart of this possibility lies the theoretical wormhole, a cosmic shortcut connecting distant points in space and time, with black holes potentially serving as the entry and exit doors. Picture a fallen tree bridging a river. The wormhole is the hollow trunk, letting you cross instantly instead of swimming the long way around. Now replace the tree with a black hole's singularity, the river with the vast expanse of the universe, and suddenly, the impossible starts to feel tantalizingly plausible. The math behind this comes straight from Kip Thorne's groundbreaking work. In the 1980s, the Nobel Prize-winning physicist explored whether wormholes, previously just a quirky solution to Einstein's equations, could be stable enough for travel. His calculations revealed something astonishing. If a wormhole could be propped open by exotic matter, a hypothetical substance with negative energy, it might create a traversable tunnel through spacetime. One end could emerge near Earth today, the other near a distant star, or even in a different era entirely. The catch, the exotic matter required doesn't exist in any form we've discovered yet, and the gravitational forces at play would likely shred anything attempting the journey. But the theoretical framework is sound, and black holes are the perfect candidates to anchor these portals. Their immense gravity could warp spacetime into the necessary shapes, while their singularities might serve as the bridges in points. Here's where it gets even stranger. Time dilation near a black hole's event horizon means that while you're hovering just outside, years or even centuries could pass elsewhere in the universe. Step through a wormhole linked to such a black hole, and you might exit not just in another place but another time. Imagine a scenario where astronauts orbit a black hole for what feels like months, only to return and find Earth centuries older. Wormholes could amplify this effect, turning relativity's quirks into a deliberate roadmap for temporal navigation. Thorne even envisioned a time machine where one end of the wormhole is accelerated to near-light speeds, creating a clock that ticks slower than its stationary counterpart, effectively syncing 2 points in spacetime that exist at different moments. But don't pack your bags for the Cretaceous period just yet. The obstacles are as colossal as the black holes themselves. Stabilizing a wormhole would require energies beyond anything we can harness, and the radiation near a black hole's throat would fry any probe, let alone a human. There's also the pesky issue of causality violations. If you could travel back in time, even theoretically, you might trigger paradoxes that unravel physics itself, like the classic grandfather paradox, where killing your own ancestor would erase your existence. Some physicists, like Thorne, argue the universe might enforce self-consistent timelines, preventing such contradictions. Others suspect quantum mechanics or yet unknown laws would slam the door on time travel altogether. Yet the allure persists. Black holes, often seen as the universe's ultimate dead ends, might also be its most enigmatic gateways. Whether through wormholes or the sheer warping of spacetime, they hint at a cosmos where time isn't a one-way street, but a labyrinth with black holes as the twisting corridors we've only begun to map. For now, the dream lives in equations and thought experiments, a reminder that the universe's most forbidding places might also hide its most extraordinary possibilities. Some stars don't just drift through space alone, they're locked in a deadly dance with black holes, whirling around each other in a cosmic tango that ends with one partner slowly being devoured. Take Cygnus X1, a binary system 7,000 light-years away where a massive blue star pirouettes around a black hole roughly 21 times heavier than our Sun. Every 5.6 days, the star completes its elliptical orbit, coming perilously close to the black hole's gravitational grip. The result, a spectacle of stellar vampirism, where the black hole siphons gas from its companion, heating it to millions of degrees and lighting up the cosmos with searing X-rays. What makes these duos so fascinating isn't just their violence, it's the delicate balance they maintain. The star and black hole in Cygnus X1 are separated by a mere 1/5 the distance between Earth and our Sun, close enough that the black hole's gravity stretches its partner into a teardrop shape. Stellar winds peel away layers of the star's outer gas, funneling it into a superheated accretion disk around the black hole. As this material spirals inward, it emits X-rays so intense they were first detected by astronomers in the 1960s, leading to the system's discovery. Without realizing it, they'd stumbled upon the first strong evidence that black holes weren't just theoretical. They were real and they were hungry, yet these dances aren't one-sided. The star in Cygnus X1 isn't a passive victim. It fights back with sheer mass, weighing around 40 times more than our Sun. Its stellar winds are so powerful they sometimes blow gas clear of the black hole's grasp, creating a turbulent zone of missed meals and near escapes. This push and pull creates bursts of X-rays that flicker like a cosmic strobe light, allowing astronomers to map the black hole's properties by studying the rhythm of its feasting. Over millions of years, though, the star will lose its mass, steadily stripped away until nothing remains but a wisp of its former self, leaving the black hole to hunt for a new partner. Other systems paint even wilder pictures. In V404 Cygni, a black hole and star orbit so closely that the star's entire outer envelope has been sucked into the abyss, leaving behind a smoldering core that still defiantly circles its predator. In LMC X3, located in a neighboring galaxy, the black hole's gravity is so dominant it forces its companion star to pulse rhythmically, as if the star itself is gasping for survival. These systems aren't just freak shows, they're cosmic laboratories, revealing how black holes grow, how stars die, and how gravity weaves the fabric of space into brutal, beautiful ballets. And here's the kicker, we might be witnessing the birth of new black hole binaries right now. When massive stars explode as supernova, their cores can collapse into black holes, and if the explosion doesn't kick the system apart, the newborn black hole might retain its stellar companion, starting the cycle anew. It's a reminder that even in the vastness of space, no star is ever truly alone. Some are just unlucky enough to find their perfect dance partner is the universe's most relentless predator. Black holes don't just feast on stars, they devour entire gas clouds in cosmic feeding frenzies that rewrite the rules of gravity's appetite. One of the most dramatic examples unfolded near our galaxy's supermassive black hole, Sagittarius A, when a giant gas cloud named G2 drifted too close in 2014. Astronomers watched in real time as the black hole's tidal forces stretched the cloud like taffy, tearing it into a streamer of superheated plasma over 100 billion miles long. What began as a compact, dusty orb 3 times wider than Earth's orbit around the Sun became a ghostly smear of ionized gas, its remnants swirling toward oblivion in the black hole's accretion disk. This wasn't just destruction, it was a rare glimpse into how black holes grow. G2's fate revealed something unexpected. Supermassive black holes might prefer gas clouds over stars for their meals. Unlike stars, which can sometimes survive close encounters thanks to their dense cores, gas clouds have no such defense. Their loosely bound molecules surrender easily to tidal forces, making them perfect fuel for a black hole's insatiable hunger. As G2 spiraled inward, friction heated its gas to millions of degrees, causing it to glow brighter in infrared and X-rays, a flare that helped astronomers track every gruesome step of its disintegration. The aftermath held even more surprises. Instead of vanishing quietly, G2's remnants flared unpredictably, suggesting the black hole didn't consume it all at once. Some material may have been flung back into space, while the rest spiraled into the accretion disk like water circling a drain. This messy eating habit challenges the old assumption that black holes swallow matter neatly. Instead, they're messy diners, slurping some gas while splattering the rest across their cosmic table. Similar feasts have been spotted in other galaxies. In 2018, astronomers witnessed a black hole in a galaxy 8 billion light-years away, shredding a gas cloud 10 times more massive than our Sun. The event produced a flare so bright it outshone its host galaxy for months, proving these snacks aren't just about quantity, they're about spectacle. These violent meals might even explain why some black holes suddenly brighten after years of dormancy, as passing gas clouds reignite their accretion disks like throwing gasoline on embers. Yet the strangest twist comes from what these events reveal about black hole environments. The survival time of gas clouds like G2 hints at the density and magnetism of the space near Sagittarius A, where even the vacuum is turbulent enough to rip apart molecular bonds. Some theorists now suspect entire populations of gas clouds might orbit supermassive black holes, their slow-motion destruction providing a steady buffet that keeps the monsters glowing faintly between star-sized meals. So while stars get all the dramatic headlines, it's the humble gas clouds that might be the real workhorses of cosmic nourishment, stretching, splintering, and shining brightly as they cross the point of no return. Their deaths aren't just violent, they're the universe's way of proving that even something as fragile as a wisp of gas can become a beacon when gravity decides to play with its food. What if every black hole is a cosmic Russian nesting doll, hiding an entirely new universe inside its crushing depths? This mind-bending possibility comes from physicist Lee Smolens's provocative cosmological natural selection theory, an idea that turns black holes from destroyers into creators, birthing whole new realities where the laws of physics might be completely different from our own. Imagine our universe as just one branch on an infinite tree of realities, each sprouting from the singularity of a black hole in some parent cosmos. The implications are staggering. Every time a star collapses or galaxies collide to form a new black hole, an entirely new universe could be sparking into existence right under our noses. Smolens's theory hinges on how tiny quantum fluctuations at the moment of a black hole's formation might get locked in as the fundamental constants of the baby universe inside. Just as genes mutate during biological reproduction, these cosmic mutations could produce universes where gravity is stronger, light travels faster, or atoms never form at all. Over countless generations, this would create a Darwinian selection of sorts. Universes that produce more black holes would have more offspring, while infertile ones would die out. The eerie consequence: our universe's laws might be perfectly tuned for black hole production, not by divine design, but through sheer statistical inevitability after countless cosmic generations. The mechanics of this cosmic childbirth are stranger than fiction. When matter collapses into a singularity, the extreme conditions might trigger a quantum bounce similar to how the Big Bang could have emerged from the collapse of a previous universe. The newborn universe would inherit some properties from its parent, but with random tweaks to physical constants, like a cosmic game of telephone where each iteration introduces subtle changes. Some versions might expand faster, others slower. Some might have stronger nuclear forces, others weaker. The key is that these baby universes would exist in their own separate spacetime, completely disconnected from ours, no way to peek inside or communicate across the divide. Critics argue this theory is untestable by nature, placing it firmly in the realm of metaphysics rather than hard science. But Smolens counters that if our universe shows signs of being optimized for black hole production, like the precise values of constants needed for star formation, it could lend credibility to the idea. And there's another tantalizing clue: the universe's initial low entropy state, a mystery in thermodynamics, might make sense if our cosmos was born from the high-energy chaos of a black hole singularity. The wildest implication: you might be standing in a black hole right now. If our universe was born inside one, then every black hole we see could be pregnant with its own cosmic offspring, an infinite regression of realities nested like layers of an onion. It's a humbling thought. The dark monsters we fear as gravitational traps might actually be cosmic midwives, tirelessly giving birth to new worlds where physics writes its own strange rules. Whether Smolin's vision holds or not, it reminds us that black holes aren't just endings, they might also be the universe's most spectacular beginnings. Consider the fate of a book tossed into a fire. The pages burn, the ink vaporizes, but in principle, every word could be reconstructed from the smoke and ashes if you had perfect knowledge of physics. This fundamental truth, that information can never truly be destroyed, is a cornerstone of quantum mechanics, yet black holes seem to flaunt this rule with terrifying ease. When a star, a planet, or even an entire civilization crosses the event horizon, every bit of information about them, their atomic structure, their history, their very identity, appears to vanish from our universe forever. This clash between quantum theory and gravity's darkest abyss is the black hole information paradox, a puzzle so profound it's divided physicists for half a century. The heart of the paradox lies in the starkly different ways quantum mechanics and general relativity treat information. In the quantum world, every particle interaction is reversible in principle. You could rewind the universe like a film, tracking every electron's path backward with perfect precision. But black holes, governed by Einstein's equations, suggest a one-way trip to erasure. Hawking radiation, the slow leakage of energy that causes black holes to evaporate, emerges as random thermal noise, seemingly devoid of any encoded details about what fell in. It's as if you shredded a library's worth of books into confetti, burned the pieces, then claimed the ashes contained no trace of the original texts. If true, this would require rewriting quantum theory itself. Stephen Hawking initially believed information was irrevocably lost, a stance that sparked one of science's most heated debates. Opponents like Leonard Susskind fired back with the holographic principle, arguing that data isn't destroyed but smeared across the event horizon like celestial graffiti. Imagine dipping a sponge into water. The liquid seems to disappear, but it's actually stored in the sponge's microscopic pores. Similarly, a black hole might encode swallowed information in Planck-scale pixels on its surface, later radiating it back out in scrambled form via Hawking particles. This idea got a dramatic boost in 2016 when Hawking himself reversed his position, conceding that information could indeed escape, though how remained unclear. Recent breakthroughs suggest an even wilder resolution. Black holes might have soft hair, not literal hair, but subtle quantum imprints left on the event horizon by infalling particles. These infinitesimal distortions, theorized by physicists like Andrew Strominger, could preserve information like grooves on a vinyl record, with Hawking radiation playing back the cosmic soundtrack as the black hole evaporates. Others propose the singularity isn't a point but a fuzzball of tangled quantum strings, storing data in their vibrational patterns. Yet the paradox lingers because no theory perfectly bridges the gap between quantum and gravitational realms. If information escapes, how? If it's preserved, where? The answer might lie in a deeper truth. Black holes aren't just testing physics, they're revealing where our current theories fracture, pointing toward the elusive theory of quantum gravity. Every bit of data they seemingly erase is a breadcrumb leading to a revolution in understanding, a reminder that even the universe's darkest corners refuse to surrender their secrets quietly. Black holes don't just swallow light, they bend it, twist it, and turn the cosmos into a funhouse mirror. This bizarre phenomenon, called gravitational lensing, transforms these cosmic voids into nature's most powerful telescopes, warping the fabric of spacetime so severely that light from distant galaxies gets stretched, duplicated, or even twisted into glowing rings around the abyss. Imagine holding a magnifying glass over a newspaper, only instead of glass, it's a black hole's gravity, and instead of words, you're distorting entire galaxies billions of light years away. The science behind this is as elegant as it is mind-bending. Einstein's general relativity revealed that massive objects don't just pull on matter, they curve the very space around them, altering the path of anything moving through it, including light. A black hole takes this to extremes. When light from a distant star or galaxy passes near one, it doesn't travel in a straight line. Instead, it follows the contours of warped spacetime, bending around the black hole like a car swerving around a sinkhole. From Earth, this creates surreal optical illusions, the same object appearing multiple times in the sky, stretched into arcs or wrapped into a perfect circle of light known as an Einstein ring. One of the most stunning examples came in 2019 when astronomers spotted a supernova nicknamed Requiem. Its light was lensed by a massive galaxy cluster, but hidden in that cluster was an invisible monster, a black hole so dense it added an extra layer of distortion. The result, the dying star's explosion, appeared not just once but 4 separate times, arranged in a cross-like pattern around the unseen gravitational giant. This wasn't just a pretty picture, it was a precise measurement of the black hole's mass, proving how lensing can unmask hidden cosmic predators. But the real magic happens when a black hole aligns perfectly with a light source directly behind it. The light wraps entirely around the event horizon, forming a luminous halo called an Einstein ring, the first complete ring ever observed around the black hole in galaxy M87, matched Einstein's century-old predictions down to the pixel. These rings aren't just artistic flukes, they're cosmic forensic tools. By measuring their size and brightness, scientists can weigh the black hole, map its space-time warp, and even test relativity's limits under extreme gravity. There's a practical side to this cosmic trickery, too. Astronomers use black hole lenses like natural telescopes to peer farther into the universe than human-made instruments could ever reach. When the black hole in galaxy cluster Abell 68 lensed a tiny, ancient galaxy behind it, the magnification effect made the distant object appear 20 times brighter, revealing details of its star formation that would otherwise be invisible. It's as if the universe handed us a free upgrade to the James Webb Space Telescope, courtesy of gravity's most enigmatic objects. Yet the strangest twist isn't just that black holes bend light, it's how they reveal the illusion of reality itself. Every lensed image we see is a lie, a photon's detour through curved spacetime that rearranges the cosmic jigsaw puzzle. A single galaxy might appear twice in the same photo, its light taking 2 different paths around the black hole, one slightly longer than the other. The result, a flickering time delay where one image shows the galaxy as it looked 100,000 years after the other, like a celestial echo. Even black holes, the universe's ultimate voids, can't help but play with light, reminding us that what we see in the night sky is never quite what's really there. Some black holes don't just lurk at the centers of galaxies, they go rogue, rocketing through the cosmos like cosmic fugitives. One such runaway, dubbed J092344, is screaming through intergalactic space at nearly 8 million kilometers per hour, leaving its home galaxy behind in a trail of ionized gas. This isn't just fast, it's 5 times the speed of most stars in the Milky Way, fast enough to cross the distance between Earth and the Moon in under 3 minutes. The culprit behind this escape, a violent game of gravitational pinball where colliding galaxies can fling even their most massive objects into the void. When 2 galaxies merge, their central supermassive black holes eventually spiral together, locked in a death dance that ends with them either merging or getting catapulted outward. In this case, simulations suggest the black holes whirled too close, too fast, and the resulting gravitational slingshot sent one hurtling away like a stone from a sling. The evidence, a brilliant streak of newborn stars and shocked gas stretching 40,000 light-years behind the black hole, a cosmic breadcrumb trail marking its path. As the black hole plows through surrounding gas, it compresses and heats the material, triggering star formation in its wake like a ship's bow wave freezing into a river of light. What's astonishing isn't just the speed, but the scale of destruction left behind. The fleeing black hole weighs in at 20 million suns, yet it's traveling so fast it could cross the entire Milky Way in a mere 15 million years, a blink in cosmic time. If something similar happened in our galaxy, Sagittarius A could one day go rogue, leaving the Milky Way stars untethered, their orbits scrambled by the sudden absence of its gravitational anchor. Yet this outcast might not be alone. Other hypervelocity black holes could be streaking undetected through the intergalactic darkness, their paths traceable only by the flicker of stars ignited in their wakes. Some might even carry trapped clusters of stars with them, stolen from their home galaxies during the chaotic ejection. It's a reminder that black holes aren't just static traps. They're dynamic, unpredictable beasts capable of being hurled across the universe by the very forces that once bound them. The ultimate fate of these exiles is as mysterious as their origins. Will they slow down, eventually anchoring new galaxies in the void? Or are they destined to drift forever, solitary giants in an ocean of nothingness? For now, this cosmic fugitive offers a glimpse into the chaos of galactic collisions, proof that even the universe's most dominant objects can become nomads fleeing the wreckage of their past. Black holes may be famous for their darkness, but some burn brighter than entire galaxies thanks to the superheated inferno swirling around them. These luminous monsters defy their shadowy reputation through their accretion disks, colossal whirlpools of gas and dust that glow with the fury of a trillion suns. Picture a cosmic blender spinning at nearly light speed, where particles collide so violently they heat up to millions of degrees, transforming the black hole's edge into a radiant halo visible across the universe. The physics behind this brilliance is both simple and staggering. As matter spirals toward the event horizon, it doesn't go quietly. Atoms rub against each other with unimaginable friction, like skyscrapers made of sandpaper grinding together at hypersonic speeds. This converts kinetic energy into heat, supercharging the disk until it emits X-rays and gamma rays powerful enough to pierce through interstellar dust clouds. Some of the brightest objects in the cosmos, quasars, are actually black holes in disguise, their accretion disks outshining every star in their host galaxies combined. The black hole itself remains invisible, but the glowing maelstrom around it becomes a beacon visible billions of light-years away. One of the most dramatic examples is Cygnus X1, a black hole devouring its companion star so fiercely that the accretion disk shines 100,000 times brighter than our Sun in X-rays. Then there's SS 433, where a black hole's disk flips direction like a malfunctioning record player, producing jets that flicker in sync with its feeding frenzy. These systems reveal a paradox. The same gravity that creates an inescapable void also generates some of the universe's most intense light shows, but the real surprise is how this glow varies. Tilted disks wobble like unstable tops, their brightness pulsing as they warp under the black hole's spin. Magnetic fields twist parts of the disk into towering loops, launching jets that shine in radio waves. And when a star strays too close, its tidal disruption ignites a months-long flare, a temporary supernova-like burst that makes even dormant black holes briefly outshine their galaxies. So while the singularity itself is forever dark, the chaos it unleashes paints the cosmos in radiant fury. These screaming disks and erupting jets prove black holes aren't just destroyers, they're cosmic artists, etching their signatures across the electromagnetic spectrum in strokes of X-rays, radio waves, and searing plasma. The next time you hear black hole, don't just picture emptiness, imagine a storm of light, chained to gravity's mightiest prison, blazing against the dark. Black holes might be the most destructive objects in the universe, but they're also shockingly simple, at least on paper. The no-hair theorem, coined by physicist John Archibald Wheeler, suggests these cosmic monsters are bald in a cosmic sense, stripped down to just three defining features: mass, spin, and electric charge. Every other detail, whether it's a shredded star, a swallowed planet, or even an entire civilization, gets erased at the event horizon, leaving behind a black hole that's mathematically indistinguishable from any other with the same three numbers. Picture tossing a library into a furnace and walking away with nothing but the weight of the ashes, the direction they're spinning, and whether they're staticky. That's the eerie elegance of a black hole's simplicity. Why these three traits and nothing else? Mass determines the black hole's gravitational pull, spin reveals how it drags spacetime around it like cosmic honey, and charge, though rare in practice, could theoretically influence how it interacts with magnetic fields. Everything else, chemical composition, shape, even the atomic structure of what fell in, is obliterated, scrambled by the singularity's infinite density. It's as if the universe has a built-in shredder for complexity, reducing the rich diversity of matter down to a trio of cold, clinical digits. But here's where the theory gets controversial. The no-hair theorem clashes with quantum mechanics, which insists information can never be truly destroyed. If a black hole forgets whether it ate a hydrogen cloud or a billion-dollar spacecraft, where does that information go? Some physicists argue it's smeared onto the event horizon like quantum graffiti, preserved in Planck-sized pixels via the holographic principle. Others speculate singularities might not be featureless points but fuzzballs, tangled knots of string theory vibrations that retain hidden data. The debate cuts to the heart of whether black holes are cosmic erasers or just really bad at filing. The theorem also has real observational stakes. When black holes collide, their gravitational waves carry signatures of their mass and spin, but no echoes of their past meals. LIGO detections support this. Merging black holes ring down to a final state described purely by these traits, like tuning forks forgetting they were once part of a piano. Even the stunning image of M87's black hole aligns, its perfect shadow smooth and symmetric, betraying no scars from the stars it's torn apart. Yet nature loves exceptions. Charge, the third hair, is almost irrelevant in practice, since black holes tend to neutralize themselves by swallowing oppositely charged particles. And if exotic theories hold, some black holes might grow extra hair in higher dimensions or under extreme magnetic conditions. The no-hair theorem isn't just a quirky idea, it's a battlefield where gravity, quantum physics, and the nature of reality itself collide. So while black holes may be the universe's ultimate minimalists, their silence speaks volumes. Behind that smooth mathematical facade lies a storm of unanswered questions, proving even the simplest cosmic objects can harbor the deepest mysteries. What if scientists could conjure a black hole right here on Earth, not in deep space but inside a laboratory? At CERN, the European Organization for Nuclear Research, physicists have been probing this very possibility with the Large Hadron Collider, the most powerful particle smasher ever built. The goal isn't to unleash a cosmic catastrophe, but to test whether miniature black holes smaller than an atom could briefly flicker into existence under extreme conditions. These wouldn't be the star-devouring monsters of interstellar space, but hypothetical quantum-scale black holes, so tiny they'd evaporate in a fraction of a second, leaving behind only a whisper of radiation as proof they ever existed. The idea hinges on one of physics' most radical theories, that our universe might have hidden extra dimensions beyond the three we experience daily. If these dimensions exist, gravity could become far stronger at microscopic scales, making it possible for colliding protons to pack enough energy into a vanishingly small space to warp spacetime into a black hole. Picture two grains of sand smashing together with such force that they momentarily dent the fabric of reality itself. That's the scale of energy CERN Collider achieves, recreating conditions not seen since the first trillionth of a second after the Big Bang. Of course, this concept sparked public panic when the LHC first powered up. Headlines warned about Earth being swallowed by a runaway black hole, doomsday scenarios straight out of bad science fiction. But physicists rolled their eyes, and for good reason. Even if these micro black holes formed, they'd vanish almost instantly due to Hawking radiation, their fleeting existence more like a quantum hiccup than an apocalyptic event. Nature routinely creates far more energetic collisions in Earth's upper atmosphere when cosmic rays strike air molecules, yet our planet remains intact after billions of years. If natural processes haven't destroyed us, a controlled lab experiment certainly won't. The real excitement lies in what these tiny black holes could reveal. Detecting one would be a smoking gun for string theory and extra dimensions, revolutionizing our understanding of gravity's quantum nature. It might also explain why gravity is so weak compared to other forces. Perhaps it's not weak at all, but diluted across dimensions we can't perceive. CERN detectors are primed to spot the telltale energy patterns of evaporating black holes, though so far, no luck. But the search continues, with future colliders poised to reach even higher energies where the odds improve. For now, Earth-made black holes remain a tantalizing what if. But the mere possibility underscores something profound. Black holes aren't just distant celestial oddities. They're a fundamental part of reality's playbook, woven into the fabric of space, time, and perhaps even dimensions beyond our perception. And while CERN hasn't created one yet, the fact that we can even contemplate bending the universe's deepest secrets to our will in a lab speaks volumes about human ingenuity and our relentless drive to explore the impossible. Black holes might hold the key to one of physics' greatest unsolved mysteries, a unified theory that marries gravity with quantum mechanics. For over a century, these two pillars of modern science have stubbornly refused to align. Quantum mechanics rules the subatomic world with probabilistic fuzziness, while Einstein's general relativity describes gravity as the smooth curvature of spacetime. Yet when these frameworks collide in the extreme environment of a black hole, they produce paradoxes so glaring they can't be ignored. It's as if the universe left us a clue in its most destructive objects, whispering that the path to quantum gravity lies in the heart of darkness. String theory offers one tantalizing solution. Imagine every particle in the universe isn't a point but a vibrating strand of energy, like infinitesimal guitar strings playing the symphony of reality. Near a black hole's singularity, where gravity becomes quantum in scale, these strings might stretch and warp in ways that reveal how spacetime itself is woven from deeper, more fundamental threads. Some models suggest the event horizon could be a holographic projection of these strings, a two-dimensional surface encoding the information of three-dimensional space, a cosmic cheat sheet for unifying the forces. But black holes don't just test string theory, they pressure test every proposed quantum gravity model. Loop quantum gravity, for instance, predicts spacetime is granular at the tiniest scales, like a pixelated image. Near a singularity, this granularity might prevent the infinite densities relativity predicts, offering a quantum bounce instead of a collapse. Then there's Hawking radiation, the thermal glow black holes emit as they evaporate. Its existence hints at a quantum layer to gravity, since it arises from virtual particles appearing at the event horizon, one falling in, the other escaping. The math works, but it creates the infamous information paradox where quantum purity clashes with gravitational erasure. The stakes couldn't be higher. If we crack how black holes handle information, we might unlock gravity's quantum code, rewriting our understanding of reality itself. It's like having a Rosetta Stone buried in the most hostile place imaginable, a cosmic vault where the very laws we're trying to decipher break down. Yet with tools like gravitational wave astronomy and quantum computers simulating black hole behavior, we're closer than ever to reading the message hidden in the darkness. Perhaps the most poetic possibility is that black holes aren't just obstacles to unification, they're the bridges. They're singularities where quantum and gravitational effects intertwine, might be laboratories for the universe's deepest secrets. Every merger LIGO detects, every photon bending around an event horizon, is a data point in this grand experiment. And when the equations finally align, the answer won't just explain black holes, it will reveal the hidden fabric stitching the cosmos together. From bending time like taffy to preserving cosmic secrets on their event horizons, black holes have shattered every expectation we ever had about the universe. Think about it, these celestial monsters transform the fabric of reality into a funhouse mirror where light loops back on itself, where a single minute near the edge could mean centuries pass elsewhere, and where the fate of everything that falls in might not be destruction but transformation. They're not just objects in space, they're philosophical puzzles wrapped in gravitational riddles, forcing us to question everything from the nature of time to the fundamental laws of physics. Take the holographic principle, the idea that every atom, every photon swallowed by a black hole leaves a two-dimensional imprint on its surface like data etched into cosmic glass. Or consider Hawking radiation, proving even these eternal-seeming voids slowly evaporate, whispering their secrets back into the universe particle by particle. And let's not forget the rogue black holes rocketing through intergalactic space at millions of miles per hour, or the mind-bending possibility that each one could contain an entirely new universe inside its singularity. Every fact we've uncovered feels less like an answer and more like a doorway to 10 new questions. So here's the real kicker. Black holes aren't just changing how we see the cosmos, they're redefining what we thought was possible. They've shown us that space isn't static, time isn't constant, and even the vacuum of space itself crackles with hidden energy. They're the universe's ultimate paradoxes, simultaneously the simplest objects in existence defined by just mass, spin, and charge, and the most complex holding mysteries we're still decoding. Now it's your turn. Which of these cosmic revelations left you speechless? Was it the black hole spinning spacetime like a whirlpool, or the terrifying elegance of spaghettification? Drop your favorites in the comments, and if this journey through the universe's darkest enigmas left you hungry for more, hit subscribe. Because when it comes to space's greatest mysteries, we've only just scratched the surface, and the next discovery might be the one that rewrites the textbooks all over again.